Welcome to Math with Professor V. In this video, I'll be solving the most recent exam, exam 3, that I gave to my Calculus 1 class. So on this exam, the topics covered include local and absolute extrema, critical values and all that, curve sketching, the mean value theorem, optimization, L'Hopital's rule, and some antiderivatives. If any of the topics that are covered in this unit are still a little fuzzy for you, you need a little bit more of an in-depth review, then head straight to the description box because I've linked every single video lecture on my channel that corresponds with all of the units that are covered in this video, okay? Or the topics, basically. But otherwise, let's just jump right in. So the first question says, find the critical numbers of the function x values only. So remember, critical values come from two places. They come from where f prime of x is equal to 0 or where f prime of x does not exist. So that means we're going to have to find the derivative of the function. But another thing you always want to keep in mind is that critical values or critical numbers have to be within the domain of the function. So let's list that out first. I feel like if you try to wait until the end to remember to check that, most of the time students forget. You're just so excited once you get a critical number. You're like, oh, sometimes we have to throw some away if they're not in the domain, so they're not really critical numbers. Look at this function here. F of x is x to the 4/5. X to the 4/5 means the fifth root of x to the 4th. And so when you're taking the odd root of some quantity, there's no restrictions there. I mean, x to the 4th, that'll always be positive, but still, we're good. Nothing to restrict. X minus 4 squared, same thing. So then I'm just going to go ahead and put as a reminder to myself, the domain is all real numbers. Okay. Now let's go ahead and take the derivative. I don't want to multiply this all out. I'm going to use the product rule. It's going to be much simpler. And from using the product rule, I can clean up my derivative better in order to find critical values. So for those two reasons, don't multiply f of x out. I'm just going to rewrite f of x here. We have x to the 4/5 times x minus 4 squared. And notice, here's my two functions. Since we're going to do the product rule, f of x is made up of a product of two functions, x to the 4/5 and x minus 4 squared. So f prime of x, the derivative, let's take the derivative of x to the 4/5 first. That'll be 4 over 5 x to the negative 1/5 times, you leave the other term completely alone. When you're using the product rule, just think the terms take turns having their derivative taken. Plus, now I'm going to leave x to the 4/5 alone. He already had his term, okay? And then now let's take the derivative of x minus 4 squared, so it's 2 times x minus 4 to the first times, don't forget the chain rule, derivative of the inside, it's just 1, but just always be on alert, okay? Good. Now here is where a lot of students struggle because we need to clean this up so we can find the zeros and where it doesn't exist. So here's my advice to you. You have two options. You could factor out the GCF right now. Most of the time, unless your algebra skills are really on point, it's a rough situation to factor out negative exponents. So let me show you a little bit of a different way. You'll get the same result, but if your algebra is not like ready for competitions, maybe try this. So f prime of x equals, I'm going to put everything with the negative exponent in the denominator. And that little 5 in 4/5 is already in the denominator. So I'm going to have 4 times x minus 4 squared over 5x to the 1/5. Good? Plus, now there's nobody over here that needs to go in the denominator. So I'm just going to reorder the term so it looks cleaner. 2x to the 4/5 times x minus 4 over 1. Good? Now my goal is, let's get a common denominator. So let's multiply this second term by exactly what I see in the denominator on the other term, 5x to the 1/5, and see where this takes us. So f prime of x equals 4 times x minus 4 squared plus, and then watch this, 2 times 5, that's 10. And then even better, x to the 4/5 times x to the 1/5. Remember, we're going to add those exponents together. 4 over 5 plus 1 over 5 is 5 over 5. So it's x to the first, and then x minus 4. And this is all over 5x to the 1/5. Beautiful, huh? And then notice now's a really nice time. We can just factor out the GCF in the numerator. So I can take out an x minus 4, only one of them, okay? And then I can also take out a 2. I can take out a 2. So let's go for it. So I'm going to take out 2, x minus 4. If I've taken out 2 and x minus 4 from this first term, I'm still going to have a 2 left and 1 x minus 4. So 2 x minus 4 to the first plus, this one's a little different. I took out x minus 4, so that's totally gone. I took out a 2, so now this is 5x. The x stays, yes? Over 5x to the 1/5. And then here we go. This is 2x minus 8 plus 5x. So I can write f prime completely factored. How lovely. 2 times x minus 4 times 7x minus 8. That's supposed to be parentheses, but it looks so deformed. There we go, much better. Over 5x to the 1/5. This is how cleaned up your derivative needs to be. So now we can find our critical values or critical numbers. Critical numbers. So f prime of x equals 0 means the numerator equals 0. So 2 times x minus 4 times 7x minus 8 is 0. The 2 is irrelevant, right? 2 will never be 0. I could divide both sides by 2 and it would be gone in a hot second. I won't even waste my time. X is either equal to 4 or x is equal to 8 over 7. And then I also get critical numbers where f prime of x does not exist. That happens when the denominator of my derivative is 0. 5x to the 1/5 is 0. That's only when x is 0. So I have 3 critical numbers. And remember, we had no restrictions on our domain. So I can report all 3 as my answers or solutions. X equals 0, x equals 8 over 7, and x equals 4. And in the problem, I told them x values only. I didn't need them to give me the y coordinates, okay? Good? Very nice. All right, let's look at another example, this time dealing with absolute extrema, not just critical numbers. So find the absolute extreme values of the function on the interval. So remember, this is also, the method of solution is based on the extreme value theorem, which tells us that every continuous function has both an absolute max and an absolute min on a closed interval. So how do we determine where they are? The procedure is you find f prime of x and all of the critical numbers. And then you make a table, plug into f of x, and compare with endpoint values. Okay. So here we go. First thing I need to do is take the derivative so I can get the critical values of f of x. So f prime of x, derivative here, it's just a polynomial. This should be so nice and relaxing. It'll be 6x squared minus 6x minus 12. There's no denominator, so my critical values are only going to come from where this derivative is equal to 0. Let me set this guy equal to 0. I can divide everyone by 6, can't I? So I have x squared minus x minus 2 is 0. And then this factors into x minus 2 and x plus 1. So my critical numbers or critical values, whatever your book calls it, are x equals 2 and x equals -1. Now, once I have that, what do? This problem's asking for absolute extremes, not local extremes. So I don't need to use the first derivative test and check where it's increasing, decreasing. That's not relevant for this problem. If you do, you'll have some nice information, but nobody asked for it. So what you go, the next step is you check this interval. Are both my critical values on the interval? 2, yep. -1, yes. So now I'm gonna make a table, x, f of x, and you plug into the original function your critical values as well as the endpoints. So I'm gonna plug in -2, -1, 2, and 3. So where are those extra values coming from? So notice here, 2 and -1 are my critical values, and then -2 and 3 are the endpoints of the interval. All right, and remember f of x was 2x cubed minus 3x squared minus 12x plus 1. So we're going to plug those in and see what we get. So if I plug in -2, you should get -3. Plugging in -1, you get 8. Substituting in 2 for x, you get -19. And 3 gives you -8. So from here, I have everything I need to answer the question. Absolute max will be the largest function value. Absolute min will be the smallest function value. So let's see, this is the absolute min and absolute max right here. So let's just summarize our answer. Absolute max, f of -1, which is 8, and then absolute min, f of 2, which is -19. There you go. Okay. So I think some students, they got confused. They forgot to plug in the endpoints. They did increasing, decreasing first derivative test, which only tells you about local extrema, not absolute. So just make sure you keep those two concepts clear. All right, onward and upward. State the mean value theorem. So I just wanted them to state it exactly how it is in the book or in the notes. So let f of x be a function that satisfies the following. Do you remember what the conditions are? So f of x is continuous on the closed interval from a to b, and then f of x needs to be differentiable on the open interval from a to b. If those two are satisfied, then there exists a number c on the interval from a to b open such that f prime of c equals f of b minus f of a all over b minus a. All right, and I did tell them they needed to know the statement verbatim for the exam, so they were warned. Make sure too that you remember the conditions. We need continuity on the closed interval, but we only need differentiability on the open interval. And then C has to be on the open interval. C cannot be an endpoint. All right, if you need more help on the mean value theorem, I have several extra videos, so go check it out. Now we're going to look at an example here. Verify that the function satisfies the hypotheses of the mean value theorem on the given interval, and then find all numbers C that satisfy the conclusion of the mean value theorem. Okay, so first thing I have to check is f continuous on the interval from a to b? So how do we address that? Well, we have a three-part definition for continuity, but we don't need to use it if f is a particular kind of function that falls into an umbrella of a theorem that we have about functions that are continuous on their domain. Almost anything you can think of, any kind of function is continuous on its domain, except for piecewise functions. So just identify f, identify its domain, and that's usually enough to establish continuity. So f is what kind of a function? Well, you might think polynomial, but then we have 8 over x, so that makes it a rational function. What's its domain? Yeah, x can't be 0. And by a theorem that we established back in the beginning when you were studying continuity, f is continuous on its domain, okay? So f is continuous on its domain, but the interval from 2 to 4 does not contain 0, so then therefore we can say f is continuous on the closed interval from 2 to 4. No problems there. Okay, next condition is f differentiable on the open interval from 2 to 4. So in order to check that, I first need to compute what the derivative is. So remember, f of x is x plus, I'm going to write this as 8x to the negative first. So that means f prime of x would be 1 minus 8x to the negative second. If you want to rewrite it, it's 1 minus 8 over x squared. So when you're checking where a function is differentiable, you check the domain of the derivative. So the domain of f prime is the same as the domain of f. It's all x's such that x can't be 0. And therefore, f is differentiable on the interval, or the intervals, negative infinity to 0, union 0 to infinity. So therefore, f is going to be differentiable on the open interval from 2 to 4 because it doesn't contain 0, so we're good. So that means we can go ahead and use the mean value theorem. So this tells me there exists, if you haven't seen that symbol before, it means there exists a number c that's an element of, or it belongs to the interval from 2 to 4, such that f prime of c equals f of b would be f of 4 minus f of a is 2 over 4 minus 2. How are we doing? Okay, good. Now f prime of c, come back here where we took the derivative. Just replace the x with c's. So f prime of c is going to be 1 minus 8 over c squared. And then f of 4, f of 2, let's plug those in. We can just do it in our head. F of 4, right here, would be 4 plus 8 divided by 4 is 2. So 4 plus 2, that's 6, minus f of 2 now, 2. 2 plus 8 over 2 is 4, so that's also 6. So actually, we could have applied Rule's theorem to this function. It's just a more specific case, but in either way, you get 6 minus 6 over 2, which is 0. So now I'm solving 1 minus 8 over c squared is 0, which means 1 equals 8 over c squared. Multiply both sides by c squared. C squared is 8. So c is plus or minus rad 8, which is plus or minus rad 2. But remember, c has to be on the interval from 2 to 4. So the negative, not rad 2, rad 2, excuse me. The negative 2 rad 2 we have to throw away, right? Because that's not on the interval from 2 to 4. So only c equals positive 2 rad 2 is an element of 2 to 4. So that's the only value we report. Okay? Good, good, good. Moving on. Is just nothing going to cooperate today? There we go. Okay, here's the big graphing problem. It was 20 points. So let's work through all the steps together. Graph the rational function using the following steps. So f of x is 8x over x squared plus 4. First thing, list the domain of f. So in a rational function, you always want to make sure the denominator is not 0. So if you check x squared plus 4, where it would equal 0, you get x squared is negative 4. That won't have any real solutions. So that means we have no restrictions on this function. So the domain is actually all real numbers, or you could say negative infinity to infinity. Okay. Intercepts. So if I want to find the x-intercepts, I'm going to set the numerator equal to 0. so that means 8x is 0. That happens when x is 0. So I have 0, 0 for my x-intercept, which is also my y-intercept. And remember, you'll only ever have one y-intercept when you're graphing a function, because if it had more than one y-intercept, it wouldn't be a function anymore, you know? So we're done. 0, 0. Fab, fab. Okay, asymptotes. So we have to consider, are there any vertical asymptotes? Well, in a rational function, vertical asymptotes come from where the denominator is 0 after you've fully reduced the function. The denominator is never 0, so that means I don't have any vertical asymptotes. Now I'm looking, the degree of the numerator is lower than the degree of the denominator, bottom heavy. So I might have a horizontal asymptote. Okay, pre-calc method would just be to look at the degree and check, oh, if it's bottom heavy, it should be y equals 0. But now that we're in calc, you should confirm this with a limit. So horizontal asymptotes describe end behavior. So I'm going to take the limit as x goes to infinity of 8x over x squared plus 4. And notice both numerator and denominator are going to infinity. You could use Lals rule, or I'm just going to multiply top and bottom by 1 over x squared to take this limit. And then I get the limit as x goes to infinity of 8 over x over 1 plus 4 over x squared. So 8 over x goes to 0, 4 over x squared goes to 0. I have 0 over 1, which is 0. So my horizontal asymptote is at y equals 0, like we suspected, right? Even if you were in pre-calc, you probably would have come up with that solution, no problem. Now, sometimes you have to check the limit as it goes to negative infinity also. Once in a while, they come out different. But in this case, like it wouldn't have made any difference if this was going, to negative infinity. I would have done the same thing, dividing by x squared. So just to save myself time, you know what I'm going to do? I'm just going to come in and put plus or minus in front, since the result would have been the same. Okay? If you get something, when you're dealing with a rational function, it'll be the same on both sides. But if you have something like a function that goes to infinity or negative infinity and it doesn't have a horizontal asymptote, check the limit the other way, because sometimes they're different. If you need more help with curve sketching, I have so many videos. I'll link them in the description where I show lots of funky cases too. Okay, so that's done. Now, I took mercy on their poor souls. I gave them the derivative because I didn't want that to like screw up their whole graph. So here's f prime of x. I wanted them to use f prime of x and just tell me what the critical values are. So we know those come from two places, where f prime of x equals 0 and where f prime of x does not exist. F prime of x is 0 when the numerator is 0. When negative 8x squared plus 32 is 0. I can factor out a negative 8, and then you have x squared minus 4 is 0. So x squared minus 4 is 0 when x squared is 4, so when x is plus or minus 2. F prime of x does not exist. That doesn't happen anywhere. That would happen where the denominator is 0. But remember, we already showed in the beginning of the problem when we were finding the domain that this quantity is never 0. So at least not in the real number system. So x equals plus or minus 2 are the only critical values. Now we have to list the intervals of increase and decrease. So to do that, let's make a number line. Here's our first derivative test coming in. F prime of x, you list your two critical values on there, -2 and 2. And then we're going to test the sign of the derivative on each of these intervals, okay? So let's pick a number between negative infinity and -2 to test this interval out. Say -3. You're plugging it into f prime of x, okay? -3 squared, that's going to be 9. -8 times 9, -72. Plus 32, the numerator is negative. The denominator, I'm not even going to plug it in because see how we have this quantity squared? The denominator is always positive. A negative divided by a positive means the derivative is negative here. So what does that tell me about f of x, the function? If the derivative is negative, the function's decreasing, okay? Next interval, between -2 and 2. Pick a number. How about 0, right? Okay. So if I plug in 0 for x into the derivative, that's why I label your number line so you know where to plug it in. That's 0 plus 32. Now the numerator's positive divided by a positive. The derivative's positive, so the function's increasing. And then last one, pick somebody between 2 and infinity. 100. 10, whatever. 10 sounds nice. 10 squared is 100. Negative 800 plus 32. Numerator's negative. Denominator's positive. Derivative's negative. The function is decreasing. So now to answer the question, we have to list out the intervals. So the function is increasing. These are open intervals from -2 to 2 and decreasing from negative infinity to -2 union 2 to infinity, right? Do we have any local extrema? Well, if you look here at the number line, it should be clear. When the function switches from decreasing to increasing, here's a local min. In fact, it even looks like it when you're drawing these arrows, fab, fab. And then when it switches from increasing to decreasing, here's a local max, which is what it looks like. So this is where my local min is, and this is where my local max is. Now we need to give the function values there though. So we have, remember f of x was 8x over x squared plus 4. So f of -2 would be -16 over 4 plus 4, that's 8, which is -2. And f of +2 would be 16 over 4 plus 4, so this is +2. So then for your final answer, just say, okay, local min, f of -2, which is -2, and then local max, f of 2, which is 2. Good? Okay, everybody did really well on this part. So now, yeah, I gave them the second derivative and then I said, list the possible inflection points. So possible inflection points, you look at the same sort of idea as when you're finding critical values. They come from where the second derivative, f double prime of x equals 0, and where f double prime of x does not exist. Okay, second derivative equals 0 when the numerator is 0. When 16x times x squared minus 12 is 0. So that would mean x is 0 or x squared equals 12, which means x is plus or minus rad 12. What does that simplify to? Plus or minus 2 rad 3. F double prime of x doesn't exist when the denominator is 0, when x squared plus 4 cubed is 0. But remember we said x squared plus 4 doesn't have any real zeros, so this doesn't apply for this function. So I have 3 possible inflection points, x equals 0, and then plus or minus 2 rad 3. Okay, good. Now we're going to list the intervals of concavity. So I want to know when the function's concave up, concave down. So then we're going to use our second derivative and make a number line to test the sign. Okay, here we go. F double prime time, label the number line. -2 rad 3 is going to be here, 0 and 2 rad 3. Okay. I always recommend labeling the number line for a few reasons. One, it reminds you where to plug in when you're testing the intervals. So we're plugging them into the second derivative. And also, since you have a number line for the first derivative and one for the second derivative, you don't want to get them jumbled up on your paper when you're looking back. Okay, so let's pick a number smaller than -2 rad 3. My students don't have a calculator on their exams. So if you're struggling, remember, this number is the same as negative rad 12. What's smaller than negative rad 12? Like negative rad 16, which is negative 4. That's a nice number. So let me plug in negative 4 into the second derivative. Now the denominator I don't have to look at because x squared plus 4 is always positive. If I raise it to the third, doesn't matter, it's always positive. So we're just going to be looking at the numerator. Negative 4 plugged into the numerator, that's going to be negative 64. And then negative 4 squared, now that's 16 minus 12, that's positive. So I have a negative times a positive divided by a positive, that's negative. So the graph is concave down right there. Let me make it there. Okay. Somebody between negative 2 rad 3 and 0. How about negative 1? Sound good? 16 times negative 1, that's negative. Negative 1 squared is 1 minus 12, that's negative. So negative times a negative divided by a positive is positive. Now it's concave up. Okay, between 0 and, 2 rad 3. Let's test with positive 1. Okay, positive 1. So this would be positive, negative. So the numerator is negative divided by positive, negative. And then over here, 4, 10, whatever. Positive, positive, boom. Concave up. So let's list the intervals now. That's what we're told to do. So the graph is concave up from negative 2 rad 3 to 0 union 2 rad 3 to infinity, and it's concave down where, let's see, negative infinity to negative 2 rad 3 union 0 to 2 rad 3. So do we have any inflection points? Remember, an inflection point is a point on the graph, point on the function, where it switches from concave down to concave up, or vice versa, concave up to concave down. Yes, all three of these are inflection points. So we need to find the y values. So let me go ahead and do that. Remember, f of x was 8x over x squared plus 4. So f of negative 2 rad 3 would be 8 times negative 2 rad 3. So that's negative 16 rad 3 over x squared. Well, negative 2 rad 3 was one of the square roots of 12. So this is 12 plus 4. So negative 16 rad 3 over 16. So negative rad 3. And then similarly, positive 2 rad 3 would just be positive 16 rad 3 up top over 16. So rad 3. And f of 0 is our x-intercept. We know that's 0. So yes, our inflection points, let me rewrite them without all the computation in between. You know, who likes to look at that? Nobody. F of negative 2 rad 3 is negative rad 3. F of 2 rad 3 is rad 3. And then f of 0 is 0. Here we go. So we have a lot going on. We had a local min, we had a local max, intercept, and 3 inflection points. So let's go ahead and start graphing. They didn't need to add anything besides what they found, okay? And I do recommend let's list out again all the important stuff that we found early on. So we found horizontal asymptote, y equals 0. We had an intercept, 0, 0. We had local min, f of negative 2, which is negative 2. We had a local max, f of 2, which is 2. And we had inflection points, f of 0, which is 0. F of 2 rad 3, which was rad 3. And f of negative 2 rad 3, which was negative rad 3. Now, rad 3 is about 1.7. So for these inflection points, just to kind of help you This is very, very crude. 1.7 times 2 is about 3.4. So this should be around 3.4, 1.7. And then this would be negative 3.4, negative 1.7. It doesn't have to be perfect though, just kind of eyeball it somewhere. So first things first, let me put in the horizontal asymptote y equals 0. So we don't forget that. There we go. And then we have that x-intercept at 0, 0. I'm just going to scale by ones. It's looking good. Local min, f of negative 2 is negative 2. There's my min. Local max, f of 2, which is 2. And then inflection points, I do recommend labeling like on there because otherwise it's really hard to see them. So 2 rad 3, rad 3. 3.4, 1.7. This is an inflection point. This is at 2 rad 3. This is rad 3. And then I have another one at negative 2 rad 3, negative rad 3. So maybe right around there. Okay, negative 2 rad 3, negative rad 3. And that's enough. I know it feels funky, but you'll be fine. So look here. This is where we have a local max. So that should be the highest point. And then if you need to go back and check what was the concavity on this interval from 0 to 2 rad 3, come up here. It's concave down. So can you draw a graph that looks concave down where that's the max? Right here. Yes? Just don't go any higher than that y value. So it's going to look like this. And then there's our inflection point. So it's going to change concavity and then approach the horizontal asymptote. So just put a little arrow. And then similar situation on the other side. We actually have origin symmetry. I didn't ask them to test, but that does help because then this is just going to be a mirror image over here. Here's the min. The graph is concave up right here. Okay. Boom. Oh, you know what? 0, 0 is also an inflection point. Let me tell the people I didn't forget. And then there's my other inflection point. It's going to switch concavity and approach the horizontal asymptote. So that's that. How did you do? Not too bad, right? Okay. Now that the graphing's out of the way, hopefully everyone relaxed. Or not. It's time for L'Hopital's rule. So use L'Hopital's rule to evaluate each limit. So the first one, we have the limit as x approaches 0, cosine 7x minus 1 over x squared. So before you apply L'Hopital's rule, you always have to make sure that you have an indeterminate form of the type 0 over 0 or infinity over infinity. If you don't have that, then you're not allowed to use L'Hopital's rule. You shouldn't. It will not give you the right answer, believe it or not. So let's check. Literally just plug in 0 for x and see where everything's going. So cosine of 7 times 0 is still cosine of 0, which is 1. So I've got 1 minus 1 in the numerator over 0 squared. So we've got 0 over 0. Perfect. Then we can go ahead and use L'Hopital's rule. Tell the people that's what you're doing. So now we have limit, x goes to 0. When you apply L'Hopital's rule, you're going to take derivative of the numerator separately and then derivative of the denominator. No quotient rule. Derivative of cosine 7x is negative 7 sine 7x. And then derivative of negative 1 is 0. And then derivative of the denominator? Good, 2x. Okay, now let's see. If I plug in 0 for x, I have sine of 0, which is 0, times negative 7. And then in the denominator, 2 times 0. So we've got 0 over 0 still. Okay, that's fine. I mean, we didn't get the limit just yet, but we can apply L'Hopital's rule again at least. So this is limit, x goes to 0. Don't forget chain rule here. No, you're not going to do product rule. This is just a constant. If there were variables, yes, do product rule. If it's just a constant, when you take the derivative, it comes along for the ride. And then derivative of sine 7x would be cosine 7x times 7. Cosine 7x times 7. I'm doing this like really broken down, divided by 2. Let's clean this up. This is limit. X goes to 0, negative 49, cosine 7x over 2. Can I plug in 0 now and find the limit? Cosine of 0 is 1. So the numerator is just negative 49 and the denominator is 2. Woohoo! We made it. Very good. Okay, let's see here. Limit as x goes to 0 from the right of x times secant pi over 2 plus x. So as x is going to 0, this first term is going to 0. Now what about secant of pi over 2 plus x? Secant of pi over 2, well, just think secant is the reciprocal of cosine, right? And we're going to pi over 2 from the right. You know what, let me just draw the graph of cosine. That might be easier than imagining the unit circle. So let me draw cosine. It'll help with imagining secant's graph. Here's pi over 2. Here's 1. Here's negative 1. We know cosine's graph starts here, goes here, and then at pi we're down at 0, right? So since x is going to 0 from the right, this is going to pi over 2 from the right. So we're over here. Hey! So we're coming through negative values, okay? So if you just want to remember secant's graph, secant has a vertical asymptote right here. Secant's going to negative infinity. So this whole term here is going to negative infinity. And 0 times any kind of infinity is an indeterminate form. Okay, should we review? There's 7 indeterminate forms. 0 times infinity, infinity divided by infinity, or 0 divided by 0, and those you can both use L'Hopital's rule for. Then you have infinity minus infinity, that's also indeterminate. 1 to the infinity, 0 to the 0, and infinity to the 0. Okay, those are the 7. So before I use L'Hopital's rule, I got to rewrite this guy. How can I make it a fraction? I say secant is just begging to go to the denominator and become cosine. Don't you agree? So let me rewrite this as the limit. X goes to 0 from the right. X over, and I can write it now as cosine pi over 2 plus x. So then now, yes, the numerator is going to 0, denominator is going to 0. Let's apply L'Hopital's rule. So we've got limit, x goes to 0 from the right. What's the derivative of the numerator? Derivative of x. It's just 1. And then the derivative of cosine something is negative sine the something. And then we use the chain rule. We check what's the derivative of the something, of the inside. Derivative of pi over 2 would be 0. Derivative of 1x is 1. So just 1. You don't have to write it, but I'm just doing it so you know I'm thinking about the chain rule all the time. Oh, it never leaves my mind, that chain rule, let me tell you. Okay, can we plug in 0 for x? So then down here, this would be negative sine of pi over 2 plus 0. What's sine of pi over 2? It's 1. But then I have times a negative. So it looks like, yeah, we're pretty much done. 1 divided by negative 1, that's negative 1. Voila. Good, good, good. Now, we did an indeterminate form that was 0 times infinity. We've done some like this. Now we're going to look in the next problem at indeterminate powers. So find the following limit. Limit as x goes to infinity of 1 plus 4 over x squared to the x. So let's see, where's this guy going? 4 over x squared as x goes to infinity, that goes to 0. So the base is approaching 1 plus 0, it's approaching 1. And then the exponent is approaching infinity. So the base is approaching 1, the exponent's approaching infinity. That's an indeterminate form. So how do we get it to where we have 0 over 0 or infinity over infinity so we can use L'Hopital's rule? Anytime you're dealing with one of these 3 indeterminate powers, you have to introduce a natural log, okay? So here's the process. And if you've never seen it before, I'll link a couple videos because it's not something you would come up with on your own. You know what I mean? So I'm going to let y equal 1 plus 4 over x squared raised to the x. And then natural log of y would be natural log of 1 plus 4 over x squared to the x. And since it's not willy-nilly, I added in this natural log, guys, okay? It's going somewhere. Since we added it in, I can move this x now to the front, okay? And then this is x times natural log 1 plus 4 over x squared, okay? And then now I'm going to take the limit as x goes to infinity of the natural log of y, which is the limit as x goes to infinity of x times natural log 1 plus 4 over x squared. And remember, I'm trying to get it to be either 0 over 0 or infinity over infinity, so I can use L'Hopital's rule, so I need a fraction. So I'm going to force somebody into the denominator because I don't have a fraction at the moment. And you never move the logarithm. He's not the one. He's going to stay in the numerator. You move the other poor little guy, in this case the x. X, you're getting sent down below to the denominator. So this is the limit as x goes to infinity, natural log 1 plus 4 over x squared. And then if I move x to the denominator, it becomes 1 over x, right? Dividing by 1 over x is the same as multiplying by x. So let's see, did that do it? Can we use L'Hopital's rule now? So x is going to infinity. That means 4 over x squared is going to 0. The numerator is approaching ln of 1. And then x is going to infinity. The denominator is approaching 0. ln of 1 over 0, yeah, that's 0 over 0. Woohoo! We can use L'Hopital's rule. Hop to it then. Tell the people that's what's happening. So we have limit, x approaches infinity. Derivative of the numerator. So when you have derivative of ln something, it's always 1 over the something times chain rule, derivative of the something. So derivative of 1 would just be 0. Derivative of 4 over x squared, maybe think of it as 4x to the negative second. So if you take the derivative, it would be negative 8 x to the negative third, or over x cubed. Good? Perfect. And then what about the derivative of the denominator? The derivative of 1 over x, remember 1 over x, that's x to the negative first. So its derivative would be negative 1 over x squared. Good, good, good. Let's clean up. So we have limit, x goes to infinity. These negatives will cancel out, okay? I'm just going to rewrite the numerator as 8 over, and then this x cubed, I'm going to distribute it through, okay? So it'll be x cubed plus 4x. X cubed plus 4x. And then I have divided by 1 over x squared, which is the same as multiplying by x squared over 1. Okay, so let's see what we've got now. Limit, x goes to infinity, 8x squared over x cubed plus 4x. You can cancel an x out from everything, so this is limit, x goes to infinity, 8x over x squared plus 4. And we still have right now, look, x is going to infinity, numerator is going to infinity, denominator is going to infinity. You could do L'Hopital's rule again. This is a limit that you learned in the beginning of the semester. You could just divide by highest power of x from the denominator, x squared. But I mean, whatever, let's just keep doing L'Hopital's rule. It's a L'Hopital's rule problem. So this is limit, x goes to infinity, derivative of 8x is 8, and derivative of the denominator would be 2x. So now x is going to infinity. We have 8 over infinity, which approaches 0. Boom. Now, no, we're not done. This is where things get a little spicy. Let me white out the page number so it's not in our way. Good. So here's the deal, okay? We just showed the limit as x approaches infinity of the natural log of y was 0. So this means the limit as x approaches infinity of the natural log of y, and y was 1 plus 4 over x squared to the x, that's 0. Well, to get my original limit, what I need to do, because remember my original limit did not have a natural log, right? I have to take the result that I just got, which was 0, and make it the exponent on e, base e, since that will undo the natural log that we added in. So my final answer is actually 1. And if you want a little bit more explanation, like where the heck is this e coming from, it's basically to undo this ln. But I break it down and show you exactly all the algebra behind this last little maneuver in the video lecture on L'Hopital's rule. Okay, on an exam, I don't need to see it. If your teacher wants it, then just do it to make them happy. But, you know, when I first show my class, I explain the process, where this e comes from. But at the end, I told them, you know, just do e raised to whatever you get, and you can tell me that's your answer. Okay, let's box it. It's beautiful. Nearly done. Next problem, optimization. So if 1,200 feet squared of material is available to make a box with a square base and an open top, find the largest possible volume of the box. Be sure to verify that your answer indeed yields the max volume. So let's draw a diagram so we can start labeling and introduce some notation. We have a box with a square base and an open top. Okay, so let me draw something. Boom, boom, boom. Okay, so the base of the box is a square. So I'll say this is x and this is x, right? Same dimensions on the base. But the height, I don't know. So I'll call this y. And I need a function that represents the quantity we're trying to optimize. So here they said largest possible volume. So what I want to do is maximize volume. Well, let's write out a formula for the volume of this box. The volume would be length times width times height, which would be x times y. So volume is x squared times y. And remember, my goal, if I'm trying to maximize or optimize this quantity, is to find its derivative, critical values, and then determine the absolute max. Well, to take a derivative, though, I need it to be a function of one variable. We're not in multivariable calc yet. I'm so sorry. So there's obviously some piece of information that I haven't used that's going to help me get rid of one of these variables, either x or y. Somebody has got to go. And that piece of information right here is the 1,200 feet squared. That's basically our constraint. That's telling us how much surface area we have that's going to limit the dimensions of this box. And it's important that the top is open because that means we only need to use 1,200 feet squared to cover 5 surfaces. So the base, which is x squared, and then we have 4 sides all around. And the dimensions of each of those sides would be x times y. Can you see? There's 1. And then the back, and then the other side here, and then the front. So this 1,200 feet squared is the surface area that's going to have to cover the base of x squared plus 4 sides, xy. From here, you look and say, who's the easiest variable to solve for? X or y? Because I'm going to substitute it back into the volume equation. Y is the easiest to solve for. So 1,200 minus x squared equals 4xy. So y equals 1,200 minus x squared over 4x. Okay, now we're going to substitute that back in here. So I can say volume is a function of x alone. And then I have x squared times, instead of y, I'm writing 1,200 minus x squared over 4x. Let's clean it up because I know next I'm going to need to take a derivative, right, to get the critical values. And right now it's looking like a hot mess. I don't want to take its derivative. So this x can cancel. And let me distribute that x now through the numerator. So I can say v of x is 1,200x minus x cubed over 4. And then let me split up the 4 just to make it a wee bit easier. So v of x is 1,200x over 4, that would be 300x minus, I'll just write this as 1/4 x cubed. Yay, there's my volume function. Great. Time to take a derivative. So v prime of x would be 300 minus 1/4 times 3 is 3/4 x squared. Critical values come from where v prime of x is 0 and where v prime of x does not exist. So v prime equaling 0 means this whole derivative would just be 0. I can move 3/4 x squared to the other side, right? Now, how would you solve for x? You want to divide by 3/4. That's the same as multiplying by 4/3, the reciprocal. So bam, 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 bam. 300 cancels with 3. This is just 100. So now I have 400 is x squared. X is plus or minus 20. But only x equals 20 is in the domain, right? It wouldn't make sense for x to be negative 20 in this case because we're making a box. If this didn't represent volume though, that would be a valid critical number. Do you get what I'm saying? It's in the domain of the function if the function didn't represent volume because our function was a polynomial, but we have domain restrictions because the dimensions can't be negative since our function actually represents volume. V prime doesn't exist. Well, no, it's a polynomial, so that's not going to be relevant. None. So my one and only critical value is x equals 20. Now I need to verify that x equals 20 indeed yields a max. And to do that, let's use the second derivative test. So v double prime of x, come over here and take one more derivative. So derivative of 300 is 0. Derivative of negative 3/4 x squared would be negative 6/4x, which is negative 3/2 x. What do we do with this? We plug our critical value in for x. So v double prime of 20, negative 3/2 times 20, that would be negative 30. All I care is that it's negative. That means my volume function is concave down at that critical value, and at the critical value, the derivative was 0. So you could see the only way for a critical value to be 0, where a graph is concave down, is when it's the local max. So boom, it does. It yields the max. And then let's see, what did the problem want? I know x is 20. Did I answer the question? They actually want us to find the volume. So I need to go back and plug in x equals 20 into the volume function here to give my answer, okay? So v of 20 would be 300 times 20 minus 1/4 times 20 cubed. 300 times 20, that's 6,000, minus 1/4 times 20 cubed is 8,000. So this is 6,000 minus 2,000, which is 4,000. This represents a volume, so the units are feet cubed. Wow, 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 what a good job. I'm going to double box it. I'm so proud. I haven't graded this problem yet, so I don't know how they did. Hopefully very well. We'll see. Okay, rest of the test has to do with antiderivatives. So 8a, find the most general antiderivative. We have antiderivative of x rad x plus rad x over x squared. So I need to rewrite this expression here so I can just go ahead term by term and compute the antiderivatives. So I'm going to rewrite this as x times x to the 1/2 plus x to the 1/2 over x squared dx. And let's see, this is going to be, remember, this is x to the first, so we can add those exponents, x to the 3/2 plus x to the 1/2, and then I'm going to split each of the terms in the numerator over the x squared down there, so we can simplify further before taking the antiderivative. So this is going to be x to the 3/2 minus 2, that's 3/2 minus 4/2. So that'll give us x to the negative 1/2 plus, what would the next term be? Very good, x to the negative 3/2 dx. And then remember, when we compute an antiderivative, you add 1 to the exponent and then divide by the new exponent. So if I add 1, I'll have x to the positive 1/2 dividing by 1/2 plus the next term, adding 1 to negative 3/2 gives me negative 1/2. And you're going to divide by negative 1/2. And then I need to put a plus c. Since this represents an antiderivative of this function, I could have some extra constant. And if I took the derivative, I'd get back the exact same expression. Okay, so always put that plus c. As a note, this is our integral sign. And this dx, they go away. You stop writing them as soon as you compute the antiderivative. So these two guys go away at the same time. They're like little bookends on your antiderivative. And then once they're gone, you put plus c, okay? Let's clean this up. So this would be 2x to the 1/2, or 2 rad x, minus 2 over rad x plus c, and we're done. Okay, good. Next one, there isn't really a lot of work to do. You should just recognize this is 9 times 1 over rad 1 minus x squared minus 2 times 1 over x dx. Whose derivative did we take to get 1 over rad 1 minus x squared? Do you remember? It's sine inverse of x, or arc sine of x. So this is 9 sine inverse of x. Antiderivative of 1 over x is natural log absolute value of x, and you just keep that negative 2 there. Just don't forget to put the absolute value whenever you take the antiderivative, and it involves natural log, plus c. So that one just checked, did you learn the derivatives of your inverse trig functions and ln? And then the last one, we have some trig functions. So what we're going to need to do here is rewrite everything in terms of sines and cosines, okay? Hopefully we can simplify before we have to take the antiderivative, because right now nothing's popping out at me. So this is sine theta times cosine theta over sine theta plus 1 over sine theta d theta. Okay, so what do we do next? We start distributing, and I can already tell this is going to be great because sine theta is going to cancel with the denominators here. So we have cosine theta plus 1 d theta. We're good. We can take the antiderivative now. Whose derivative did we take to get positive cosine theta? Sine theta, right? Whose derivative did we take to get 1? Just theta. And then put plus c. Not x. You have to respect the variable of the problem. So if we're using theta as our independent variable, then antiderivative of 1 would be just theta. Good. Okay. Shall we continue? Here we go. Find the curve y equals f of x in the xy plane that has the given properties. So it says f of x has a slope at each point given by negative 1 over x squared, and it passes through the point 1/5, 11. So at this point in your calculus career, when you hear slope, your brain should start going to derivative, right? So what this is telling me is the function has a slope given by this expression. That means f prime of x is equal to negative 1 over x squared. Ooh, okay. And then what's the problem asking? Find the curve or find f of x, the original function. So I know what f prime of x equals. If I want f of x, how do I get there? I would take an antiderivative, yes? Okay, so let's rewrite the derivative so it's a little easier to figure out the antiderivative. This is negative x to the negative second, yes? So the antiderivative f of x, remember, you take this exponent, you add 1, and then you divide by the new exponent. This negative that's sitting outside, he's just going to hang out for now. So you have negative x to the negative 2 plus 1. So this new exponent would be negative 1. I'm going to divide by that new exponent, and then don't forget plus c. So how does this simplify? These negatives cancel. I just have x to the negative first plus c. That's my f of x. Let me write it nicer. 1 over x plus c. I can find c. Yes, because they told me this point is on the function. So I'm going to substitute in 1/5 for x and 11 for y, or for f of x. So f of 1/5 is 1 over 1/5 plus c, and this all equals 11. So 5 plus c is 11, so c is 6. And then now I can substitute that back in here and then report for my final answer, f of x is 1 over x plus 6. Beautiful. Okay, last problem, little particle motion problem, dealing with antiderivatives again. So given the acceleration, initial velocity, and initial position of a body moving along a coordinate line at time t, find the body's position at time t. So what they want is the position function. They want s of t. So they gave me acceleration, a of t, which is 20 cosine 4t. The thing to remember is acceleration is the second derivative of the position function. So this is the same as s double prime of t. So to get back to position function, I'm going to have to take two antiderivatives. Since this is the second derivative, you got to undo each of them. So first, let's take one antiderivative. That'll get me back to s prime of t. Now here's where you have to be careful. Antiderivative, the 20 doesn't do anything. Just leave him alone. He's minding his own business. So we need to be a little bit careful because this is cosine of 4 times t, not just plain old cosine t. So let's think. I know the antiderivative is going to involve sine 4t, but let's see exactly how. When we take derivatives, say I asked you to take the derivative of sine 4t, what would it be? It would be cosine 4t times 4, right? Because of the chain rule. So you would have 4 cosine 4t. So what if I said, well, this 4 shouldn't be here, right? Because I'm just talking about antiderivative of cosine 4t. Whose derivative would you have to take? You'd have to take the derivative of 1/4 sine 4t, right? Because derivative of 1/4 sine 4t would be, you'd keep the 1/4, then you would have cosine 4t times 4, and then these cancel out, and you get cosine 4t. So here's like the easiest way to think about it, in case that was just too much over your head. When you take derivatives and you do the chain rule, and it's just going to be a constant, all you do is multiply by that constant, right? I'm taking the derivative. Here's an extra constant in front of the argument, so I'm going to multiply by that constant. What's the inverse operation of multiplication? It's division. So if you're taking an antiderivative and there's a constant in front of the variable, you're just going to divide by it. That's the easiest way to think about it. So antiderivative of cosine 4t would be sine 4t divided by 4. And then put plus c. So then I get s prime of t equals, this is 20 over 1, 20 and the 4 cancels, this is 5 sine 4t plus c. Now I can find c because they gave me the initial velocity. Remember, s prime of t is v of t. And they told me right here, v of 0 is -4. Okay, so v of 0 would be 5 times sine of 4 times 0, which is 0, plus c, that's -4. This is just 0. So c is -4. So I can say the velocity function is 5 sine 4t minus 4. Okay, remember this is still s prime. We want s of t, so one more antiderivative. So s of t would be, remember the 5 just hangs out, antiderivative of sine 4t, just go, whose derivative did I take to get sine something? Negative cosine something, And then I'm going to divide again by the 4. Basically, to undo the chain rule, we divide by those constants. Divide by 4. Antiderivative of -4 would just be -4t. And then I pick up one more constant. I already used c, so just put plus d. Okay? This is a hot mess. Let's rewrite it. S of t is -5/4 cosine 4t minus 4t plus d. Now I can find d because didn't they tell me? Yes, right here. S of 0 is -2. So let's go ahead. S of 0, that would be -5/4 times cosine of 0 is 1 minus 4 times 0 is 0 plus d, that equals -2. So -5/4 plus d is -2. Let me add 5/4. -2, that's -8/4. Plus 5/4 would be -3/4. So d is -3/4. All right, so then now we can put it all together. I can write S of t is -5/4 cosine 4t minus 4t minus 3/4. Boom. Okay, very good. I did put an extra credit. Do you see it? Find the limit. No partial credit. They just had to get it or they don't get it. It's extra. I won't solve it right now. I'll let you try it out. If you want to see the solution, let me know in the comments down below and I can record it separately. But that concludes exam 3. So now they're just gearing up for the final. We're moving through the last unit, which just has a few sections, and I don't do a separate test on that. I'm just going to put everything on the final. The final's cumulative. And I probably won't make them graph though again, like the long graphing problem, since they just did that. So hope you enjoyed the video. Give it a thumbs up, subscribe if you haven't already. And like I said, if you need a review of any of the topics that were in this video, then head to the description box. Also, you could just check out the playlists on my YouTube channel because I have everything organized, like Calc 1, Calc 2, Calc 3, even if you need a pre-calc review, for crying out loud. That's so normal. I got you. And also, please follow me on Instagram, TikTok, Math with Professor V. I love you all. I'll be back sooner than later. Bye.